Okay, guys, home stretch. This is pre-lab 2 for our present with photoelectric effect and radiation and Ballmer lines. And I guess I'm always, 1L, I thought so. Okay, so once again, there's a lot to absorb. I've been working, believe it or not, I've been working. It's 3 o'clock. I've been working on this since 9 this morning to try to keep this easy to understand. So anyways, like on the order of 100 years ago, we didn't really know what the atom looked like, and I guess Bohr, let's see, so J.J. Thomson in the early part, we did the O-REM, so we understood that there were electrons, and Rutherford scattering showed us that there was a heavy nucleus in the middle and the electrons were around them. Okay, so we were trying to figure out observations, and a lot of this had to do with these so-called emissions spectra, and you see every element, and I imagine molecules as well. Notice these are sodium's not a noble gas, but helium and hydrogen and neon are noble gases, and these are things you can put into a electric arc tube. Well, that's funny. I don't have one to show. Well, it's here on the left, and I call it the era of counting, and people were looking at all this, and in fact, this started before. This was started in the 1800s, and people were looking at all kinds of elements. And in fact, helium was discovered this way. You can get hydrogen from taking a couple of electric wires, plus minus of a battery, dunk them in some water, and one of them bubbles up hydrogen, one bubbles up oxygen. This is how they discovered the law of proportions, H2O. Of course, you had to assume that the ideal gas law, that at STP, 1 mole of gas occupies 22 liters, or at least all gases occupy the same amount of volume, no matter what they're made of. And so if you get twice as much H2, so you get twice as much hydrogen as you got oxygen, then they thought, okay, it must be H2O. So in any event, the turn of the century was also where we looked at all these counting experiments and measuring things, counting things, not just counting, as like last week with Poisson's statistics. And people started studying these things and beginning to realize that the classical interpretations didn't work. And I didn't finish the thought. So people started, of course, you got a big bright ball in the sky called the sun, and you can in fact find evidence of these elements, but there was this mystery here that it was named helium because of Helios, one of the mythological gods. And let's see, I'm just making a setting here for my tablet. It's quick and dirty settings here, so I can not make sure the tablet works the way I want it to. Okay. So helium is from Helios, the sun, because helium, it turns out, you can mine from the ground. You can't create it easily because it's a noble gas. Excuse me. And it doesn't combine with anything. but it is mined. Hydrogen you can make your own, all the rest. So if you liberate some hydrogen or helium into the atmosphere, it actually escapes into outer space. Isn't that a trip? So this is how helium was discovered. So anyways, now we're trying to understand how these things can be made, and we have now a model of the atom. And so we need to say, how can we reconcile our model of the atom with the spectra that we observe? And so there's an issue with having electrons go in circular orbits because the force of attraction is so high. And remember, you learned this, F equals K Q1, Q2. And you don't have to write this down necessarily. And the force of attraction, and then you set to make something orbit, you set it equal to the centrifugal force, centripetal force, if you like. And this force is so strong, as I've told you before, much stronger than gravity. At the distances involved, v would have to be actually faster than the speed of light, first of all. Second of all, if they did orbit like this around with some instantaneous velocity vector, because they're bending, they would be radiating so-called synchrotron radiation, and they would quickly decay and fall into the nucleus, which we know they don't do. And so there was all this back and forth. So Bohr just said, yo, guys, we're going to assume that the electrons are in circular orbits. And not only that, each orbit has a discrete energy, and we're going to label them 1, 2, 3. And you guys know that this is the that's the first quantum number, right? You have 1s, 2s. That's what these are. They're circulars, right? Remember that? And then 1s, that's it. But 2s, then there's also 2p. So every time somebody found something new in these spectra, they added another quantum number. But we aren't there just yet. So we call these the primary quantum numbers, 1, 2, 3, etc. So each one of those has a discrete energy. And electrons can only jump from one level to another. Now, they can certainly jump more than one. They can jump 2. But if they jump down, they emit a photon. That's what this little symbol. This is a kind of symbol for a photon. It's a gamma, a lowercase gamma, is the Greek letter. But if they either can absorb, the incoming light has to be of certain wavelength, hence energy. So E equals H. That's the frequency. This new symbol. Or equals hc over lambda. And so if a jump occurs, there has to either have been an emission or an absorption of a photon that matches the energy between the two levels. So we're just going to say emission, so that's what we're going to be looking at. So the important thing to take away is the 3 Bohr rules and what this delta E is. In this case, I jump down. We're always thinking in this lab about jump downs. Okay. Now I wanted to save this as annotated so that I'll post the unannotated one so you guys can use the illustrations if you want. Annotated. Okay. All right, and I just have to delete a few of them. So anyways, if we look at a hydrogen, that there are different people studied these. I don't know exactly how you would study the Lyman series and the Passion series. Notice they all jump down to level 3. These all the various levels and 2. Also notice that they get closer together as you get further out. That's because it's a so-called continuum. So it's quantized when you're close to the nucleus, but when you get far away, the levels, the differences are so tiny that we don't generally notice them, and that's the transition from the quantum world to the so-called classical world, where everything is just a photon can have any energy, not some discrete energy. And then this Lyman, so these would be really long wavelengths. So in the red end of the spectrum, or infrared, things we can't see, these would be ultraviolet. And then so that's why these discharge lamps do make a little bit of UV, and you would get a tan from them eventually. Although they're in glass tubes, glass blocks UV, just as a point of knowledge. So the one we're going to look at is when they decay down to n equals 2, because they're the easiest. We only need our Mark 1 eyeball. And you see they go red to this kind of cyan to a violet and a very dark violet. And there's some kind of problems I'll show you later on about getting a set of these numbers, but we don't worry about that just yet. So we're going to study, for your logbooks, we're going to study the Ballmer series. And so all these things, every element has a fingerprint. And so by studying these transitions, and this is hydrogen. I don't know if I made that crystal clear. Yeah, this is of hydrogen. Hydrogen is the lightest element. It's 1 proton and 1 electron. And so it turns out that these things are, we'll hold off on that for a second. So it turns out, stop, Harry, just first go through. So he came up with this. This is Bohr's equation, and 13.6, you see that's the amount of energy that it takes to get an electron when it's in the bottom energy state to ionize it, to drive it away from the proton. Right, so hydrogen is a proton and an electron. So if 1 over the final energy level minus 1 over the initial, so this is always going to be less, so it's always a positive number. Even if they switch, the numbers were changed and it's a negative number, that just means it's absorbing it. It's no big deal. And for us, it's always going to be 1 over 4. And then with playing with units, and so these are all in EVs, electron volts, which is not an MK. Is it? No, it's not an MKS unit. And so this Rydberg constant you see there, that's in MKS. And that'll get us 1 over lambda. That's funny. I guess it must be in meters. Yeah, 1 over lambda in meters. And it turns out, you see, it has the high H subscript. As you get to heavier and heavier elements, you have to correct it. What happens is in hydrogen, when the electron moves up and down, the proton moves a little bit too. It's like conservation of momentum. And you have to take into account and use the so-called reduced mass. But we're not going to deal with it. We're just going to use that Rydberg constant as it is. Excuse me. Just another way of looking at it. you see it's it can absorb as well as emit. And in fact, this is odd because there's no yellow line here, so I'm not quite sure if this really is. Oh wait, this is no, it's hydrogen. It has to be. Okay, so this is the basic thing that we're going to investigate. Objectives. Gosh, isn't that something? I worked on this so much, right? So the objectives are learn about the Bohr model, and we're going to test the Bohr model, test the Bohr model and Bohr's equation, and then learn about prisms. So this is we're going to learn about dispersive media. A prism dispersive. Let's just start over again. Dispersive, and that just means it's wavelength dependent. So the index of refraction of a prism is different for every wavelength. In the optics lab, it's special glass that the index of refraction is constant. And then we're going to use that going to use that. We're going to know. Let me pause this for a second. Oh, I lost track of the little doodad. Oh, there it is. All right, so we're going to learn how to use a spectrometer. And we're going to make a plot of lambda and n, and we're going to get a calibration equation, and we're going to do a fit to get it, and then we're going to measure, or I don't know what the right word is, measure an unknown element. Isn't this funny? I probably have a list of objectives. We'll let them refine this list. And unknown element. So, in fact, we're going to use helium to calibrate it, and then look at hydrogen. Because this is the Ballmer series. I'm trying to. Just for a moment, take a look at this. Is the lab manual they want to give you, and it's hard to believe 2013 they didn't have. This is like Xeroxed, right? And it's so minimal. It's really lame. And so I've only taught it a few times, so I'm trying to zero in better and make it more meaningful for you guys. Oops, I didn't want that to go away. Here we go. Okay. Solicit a few objectives. Okay, so we got the concept of energy levels and photons. Now we look at, we all know, I assume we all know that a prism makes rainbows, and you shine white light on it, and you get this continuous rainbow-looking thing. I showed you how rainbows are made with the internal reflections of the inside a water droplet. And in that case, that's the total internal reflection. That's what makes it dispersive. But in this prism material, it is about the medium being dispersive itself, not the reflection, the effect of having a slow to fast reflection. In the water drop, you have at least two of those types of reflections. So you notice that this one is set up in a special way so the angles are equal. But for your logbook, the idea is that you have two normals. You have fast to slow, slow to fast. So when you go fast to slow, you get closer to the normal. You go slow to fast, you get further away. So you see that bend. And one notices that the angle is different for the red light and the blue light. And there's our playlist. Where is it? Ah, here we go. So this is pretty cool, this guy here. You can maneuver that. This, you can also see how a lens works. Well, this way, and you have to put it in parallel light, I suppose. And this is whole business of a focal point. But anyways, let's stop playing. And of course, I had that all nicely set up, and it's not. I don't know if this will move up and down. Okay, so if you watch, I'll move. There's a slider. It's off the screen. You can't see, and I'm changing the color, and you can see this thing changing its angle a little bit. Right, so it's different for each color bends a little bit differently. So when you have your end from on either side of the medium, the ends, when you're in the glass there, you're using a wavelength dependent end. Now, so you can derive an equation, and the equation, it's possible when you assume that the two angles that it's basically that there's a straight line across this prism, so that means the angle at each interface is equal. And so that's the so-called minimum delta. And here, the apex angle is important. We don't have the ability to measure it with the spectrometer they gave us, which I found this really neat lab exercise where it would really help you to get familiar with the spectrometer, but ours are very simplistic. I mean, maybe that you like that because it's easier to use, but it's not as much discovery potential. So if we assume that the apex angle is 60, it's a equilateral triangle, then we end up with this equation here. And divide by a half, right? So that means I multiply this by 2. No wonder it's something I was working on something else, a spreadsheet, and I thought never mind. I'm digressing. Equals 2 times Control V. There it is. So that's our equation here. Now, one thing we have to make sure that we're measuring that angle, because see what happens here. I've got this set up, so that the two angles are equal, and with blue light. And notice that when I do it with the red light, that the prism is tilted a little bit. And so I can actually show this in the sim that what you do is, you see, watch on the right here, this guy here, and see that it reverses at a certain point. So we're trying to get this thing right where it's not moving. This is basically what we're going to call our error in our measurement as well. So we'll go over it in class, but every time you look at a different color, so you'll be looking at it from this end, you've got to make sure that you've got this set up so you're getting delta min. And then, and I got our new equation here. I got let's see, copy. This is awfully exciting. And so we don't even need these guys anymore. Let's do it the long way, of course. Control V. All right, here's our, oops, two ends. So we're going to be measuring angles. We're going to know the wavelength of the lines we're looking at, and then we're going to calculate n. And if you plot it, you'll see something like this. So what we're going to do is plot 1 over lambda squared, and this is called a Cauchy relation of all things. And I'm not going to get into the derivation. I couldn't even find one, but I figure it's probably not trivial. But this equation below here follows from this equation. Has to do with behavior of sines. And I would imagine there's some limited range. I'm not certain. Although you notice that's just n. There's no wavelength involved here. But we know it's in there because each of the colored lines we're looking at. Okay, so this is what it looks like. You see there's, this is where the light comes in. There's an adjustable slit you'll learn about. The prism sits here. This prism can be rotated. Remember, we need to do that. This inner table here. And then the telescope rotates around, and then there's this thing you're going to hate, the vernier down here. And there's even a magnifying glass on it to help you read the vernier. And here it is in schematic form. Light source, collimator, I don't know. It just means it keeps the light as a narrow slit. The prism table can rotate, and the telescope rotates. And the way it's set up, it's the angle from straight through, right? So what we're going to do is we're going to remove the prism temporarily, set the telescope here, and we're going to get the whatever the reading is at the so-called 0, because I went and played with it. It's not set up to be 0, so we have to write that down. And then put the prism back and take our measurements. And then, so you're going to need to learn how to read this vernier. So there's a short video here. It's also, where did it go? Here. Oh, this needs to be, I see. Now this is our playlist, and you see there's this guy with an Australian accent. Maybe that'll hold your interest. This video I'm making right now will show up here eventually, but you should look this up. I made this picture here so that you can, he'll go through, explain how to get the reading. And I'm sure I'll have to go over it again with you guys in class. Okay, so we're going to be armed with this list of numbers. I got, this is what originally, I think that means faint red, yellow, green, BB, bright blue, violet. See, they don't, here's okay, so there is a key here. Faint red. We'll see. I have this guy. It's too bad. I can't find one. See this one here? Okay, that's probably red, but I'd like to have one that's a 1-to-1 match. And every time you find one of these things, it's a little bit different. All right, so I think this is the last slide. And so we're going to be given these wavelengths for each one of these colored lights. And I'm going to study this more on tomorrow, Monday, and try to come up with a definitive list of frequencies. You're going to measure the straight through position in degrees, minutes, and then you convert it to decimal angle. This is a holdover from, like, instead of having tenths of cents and dimes and 20-cent pieces, we've got quarters, and our measuring system as eighths. So we have degrees and minutes. Angles are degrees, minutes, seconds. Well, that has to do with the fact that longitude lines, the north-south lines, have to do with time. Each degree of longitude equals 4 minutes of time. So 360 times 4 minutes gets you 24 hours. And it has to do with navigation. So it isn't even about the revolution and quarters and dollars, so forgive me for that one. But it definitely has to do with the development with navigation. But we need a decimal angle, but we just let the spreadsheet do that. So you guys are going to be writing down degrees and minutes for the center of each one of these. There's a crosshair. And okay, so the last thing is, too, not only should you watch the video, where is it now? The how to read it, this one here, this woman is, there's some things about this that we can't measure, but she shows you how you put the crosshairs. She shows you how to get delta minimum with the real spectrometer, and how to set it up, how to adjust the slit, something I can't do right now, and except in class, and which I will. But you watch this gal here, and she will give you an idea of how this all works. Okay, so I'm going to get this up to, I'm going to stop it and get it up to YouTube.